Hi, welcome to our brief introduction to the Laser Lab team. This talk will be given by both Alice and myself. You'll be hearing from both of us through this as we cover give a brief overview of some of the different areas that we work in. So within the laser team, we focus on all sorts of materials, metals, plastics, woods, glasses, etc. As a general overview of the sort of things we can do on all these materials, we're interested in surface structuring, so creating micro and nanostructures, anything that influences the wettability and adhesion properties of surfaces, influencing microbiological control, photon management, which is modifying materials so that you can control and direct light where you want it to go, as well as things such as sealing, whether that's plastic to plastic or dissimilar materials, so plastic to metals and that sort of thing.
An example application of our current work is bioadhesion. The adhesion and growth of biofilms are well known to cost the UK industry billions of pounds each year. This could be due to product contamination, energy losses, equipment damage. When we think about hospital environments, this is through patient infections through indwelling devices. And actually, it's been estimated that hospital-acquired infections can cost the NHS up to 1,000 million per annum. However, it's not all doom and gloom. On the flip side of this, biofilms are not all bad, and in some cases, the adhesion of bacteria to surface is being used in various industries such as waste management systems, biocells. So depending on what the species we're actually looking at depends on whether we actually want them to adhere or to actually have some form of surface repellent or a bactericidal effect from the surface to prevent this or stop this biofilm formation, this bacterial adhesion. So how bacterial cells adhere to the surface and proliferate and how surfaces influence the surface, it actually remains as a really complex area of research. We do know the physical properties of a surface regulate bacterial cell attachment and physiology, and so this is going to play a key influencing factor in the early stages of biofilm formation. So surfaces that influence bacterial attachment through their physical structure is presenting a key area of research for many different environments and purposes, and this has been my main motivation for my specific research. More recently, I've been investigating the use of laser engineering, so laser surface engineering, in particular industry-ready CO2 laser applications to engineer localized patterns onto polymers with a particular focus on polyethylene terephthalate, PET, and PTFE. And the example of the textured surfaces on a PET film is shown on the left in comparison to the as received material, which is shown on the right. So far I've been able to model the wetting characteristics in order to understand how the water is interacting with the surfaces, with the idea that the greater the wetting property, the more likely bacterial cells are adhere. Now, the specific work that I've been doing is important because it's not just looking at the basic roughness of the surface and the apparent surface contact angle, which can be misleading in the literature, and we see a lot of conflicting reports from this, but it's considering a range of surface features and the impact this has on the adhesion of the droplet. Now, you can see in the images on the slide that the texture surfaces are shown to be more hydrophobic, but in actual fact there is a significantly higher bacterial load to the surfaces in comparison to the as received. So we cannot in isolation use the apparent contact angles and the roughness measurements to predict candidates for preventative or encourage bacterial loading. We have to look at a larger range of surface parameters to do this. Now, taking this further to understand how specific species interact with surfaces, I have been able to model the interaction energies between the surface and, in particular, the species that's shown in front of you is E. coli. And this was used to predict the likelihood that a particular bacterial species will adhere to the surface or be repelled from the surface upon contact.
Moving on to our work on food packaging, we've had some experience of using lasers to seal food packaging. We were using a CO2 laser for that. Now, unfortunately, a lot of that work was covered by NDA, so I can't talk about it in great detail. But our general findings were that these sort of lasers can produce strong, almost weld-like seals between plastic materials, and they don't have particularly great heat-affected zones, although that does depend greatly on the actual plastics that you're sealing. You can produce kind of non-weld-like seals, but they're significantly lower seal strength. They won't last as long, and they won't be able to withstand as much mechanical pressure. It can process very high speeds. I mean, our CO2 laser is relatively low power, but even that was capable of creating some fairly strong looking welds at a fairly fast speed. It works with pretty much any polymer, so your common ones, polyethylene, polyethylene terephthalate, polypropylene, that sort of thing, and most others you can think of. There's also the potential, we didn't do it for this, but it's possible to do what's called transmissive welding. So for that, you use a laser wavelength that's not absorbed by the transparent polymer on top, but is absorbed by the material underneath. So that's often a non-plastic, like a metal, or it can be suitably doped plastic. So if you've got the right additives in a plastic, so it absorbs the right wavelengths, then you can pass a laser through the top material, heat up the bottom, and then that fuses the two together. And here's just an example of a roughly sealed food tray, all done by our kind of, I guess, non-optimized in-house laser, but it seemed to work reasonably well. Other stuff that we do based on polymers, we've worked on creating high haze substrates towards improving photovoltaics, so trying to scatter light through the photovoltaic material to improve absorption. We've done texturing of PTFE, making it completely non-wetting. Obviously, PTFE, or Teflon to use its brand name, is often applied to pans and other materials as a non-stick coating. But even though it's quite hydrophobic, it's still there's still a level of adhesion. We've been able to use our lasers to make PTFE completely non-wetting. We also engineer the surfaces of other polymers, so again, polyethylene, things like nylon, PEEK for different applications, as well as looking at embedding metal nanoparticles within polymer surfaces. So to do that, we generally deposit a very, very thin nanoscale layer of a bulk material, process it with a laser, and then the metal coating is kind of subsumed within the molten polymer, fracturing up into nanoparticles, which can then interact with things like, again, bacteria in different ways. Here's a few of our chapters and publications and conferences that we've published on or presented at based on polymers. And other than that, thanks for listening to us. If you want any more information on what we do, we have a website, it's chesterlasers.org, or perhaps better yet, contact us via either our emails or through the wonderful people at Crest.